minutes or so. And thank you so much also for being here. This is the last talk of the workshop. So please go ahead.
Sure. Hey, everyone. It was great to be at the Simmons Center last year. I was working on the smart contracts for Algorand before last summer, and it was continuing while I was at Simmons. We're continuing making progress, and I'm happy to report our design and prototyping and the interesting things that we found. So this is the joint work with Morris, Leahy, Victor Lachanko, and Luba Schreier, speculative smart contracts. Right. So at the beginning of this year, I just realized that the assets locked up in the smart contracts, mainly on Ethereum, exceeded $1 billion in the DeFi markets, which was an all-time high. And I think during the summer, this amount has more than doubled, although I couldn't find a consistent number about whether it's 3 billion or 8 billion or even more, depending on the source. But you get a sense that this is really of high stake. Now, in terms of smart contracts, at a very high and not so accurate level, you can imagine it as a vending machine that a user could input a dime, and the machine doesn't have a person operating, but has some built-in logic that would recognize input and process and return soda for the user. A smart contract is not so different in the sense that it operates on some coins and trades some tokens or crypto assets. But the trading is controlled by the underlying logic, not by people. What's different is the distributed nature of the smart contracts from a vending machine. A vending machine is basically a single machine perspective, but on the blockchains, both the consensus and the smart contracts are governed by some entities on the blockchain. And in the existing system, mostly smart contracts are executed in the critical path of the blockchain for generating blocks. Pictorially, you can imagine it like the following. The users would submit regular payments transactions and smart contract transactions. Some blockchains have propagation network, some are via private communication, but the point is that there will be a set of users randomly selected or prefixed. Those users are governing the generation of the blocks, and those users are also the ones that execute the smart contracts code with the virtual machine. In Algorand, they are called consensus committee. Some blockchains called miners, validators. We'll refer to them as consensus committee, but you get their role. And then those committee will finalize the output, the states in the blockchain, including both the simple payments and the smart contract transactions. The smart contracts, since they encode arbitrary user-defined code, their size, here the size is not really byte size, but the execution time spent in terms of running them could be much higher than the simple payment. The point is that here, since they all land up in the same way, simple payments are waiting for contracts to finish execution and are therefore blocked by them. It is like in a supermarket, instead of having everybody shopping around, there is one entry and exit point, and the people need to go. So even if a buyer only wants a bottle of water, he will still have to wait for another shopper who has a super long shopping list. So this is what's going on in today's smart contracts. seen a surge in the usage of smart contract in DeFi. This caused congestions and the gas fee has surged. I would like to term this as a good problem to have. This problem happens because our popularity has increased. But because of this congestion and high fees, also the fluctuation of the fees, making them unpredictable, we would like to address the problems from a different approach, which is in order to achieve scalability, to scaling the smart contract and without affecting the blockchain's main block generation, we're going to take a different approach. And that different approach comes from our observation that a lot of the smart contracts existing today do not need to be processed, or do not have to be processed at layer 1, namely the consensus protocol. And there are a lot of them forming a long tail. For example, there are contracts that are too big with data intensive apps. For example, a private security offering that needs a large whitelist know your customer database, may even have a blacklist database that can be huge. Some contracts may be too long, computation intensive. A lot of cryptographic applications would fall into this category. Even though the execution times have been increasing in the past years, there's still a gap between how fast they are and what a normal operation would take. Another category of smart contracts, probably something that is sort of weird in the sense that they come up in all of a sudden, like CryptoKitties. CryptoKitties is sort of non-fungible tokens, but not the standard ones. They have secret formulas about how the DNAs of the kitties could mutate, and some intense computation involved. They were such popular application and crashed Ethereum in 2017. But they surged suddenly and they almost disappeared suddenly. It's hard to prepare for layer 1 to predict what would come like this. And by the time people are prepared, they probably have disappeared too. Another type of smart contracts that we find better not in layer 1 are with software engineering efforts. Some contracts functionalities are too complex. You may prefer to have a higher level language instead of assembly level. Some modularity would be good to decompose the tasks. Some involve different contracts controlled by different entities. In order to engineer them, it's better to have a well-supported software engineering environment rather than write directly in layer 1's probably lower level languages. So after we did a lot of investigation about existing smart contracts and thought about what's the best thing to do for scaling, the solution we want to do is to move the arbitrary user-defined code out of the critical path of the consensus protocol. And we are doing this by having the smart contracts to be speculatively executed relative to some a snapshot of the blockchain and only finalizing their effects on the blockchain at a later time. So I'm going to briefly talk about those three things. One is the architecture, how it look like in general. And one is we'll dig deeper about how a speculative virtual machine would differ from a non-speculative virtual machine. This is a single machine perspective, just from a single node, what should be done. And then from the distributed perspective, how information is replicated and communicated in a network. This is a different flavor from the theoretical studies in the sense that we are not proving theorems. This is really a cross-disciplinary project with programming language, database, a little bit distributed computation, formal verification. So a lot of different approaches from rigorous mathematical proofs. So in terms of the overview, let me first say something about what transactions are supported directly in the layer 1 of Algorand blockchain. Ethereum's blockchain supports simple payment transactions, and everything else will need to be done via smart contracts. Algorand supports simple payment transactions too, something like this. Alice is paying 5 agos to Bob. That's a payment transaction. Algorand supports some other components directly in layer 1. For example, atomic transactions is a way for the user to specify that certain actions need to happen in an atomic way. For example, Alice and Bob want to do a swap, a atomic swap. In Ethereum, they will have to use hash and time locks. On Algorand, they would both sign such a structure with 2 transfers. And the blockchain would treat it as the first happens if and only if the second happens. So this is considered as atomic. There is also the layer 1 smart contracts, which is designed to be a very simple language, a script, a stack language, assembly level. We call it TEAL, Transaction Evaluation Approval Language. The point is that it has a small set of opcodes and it does basic things so that it does not become the bottleneck on the blockchain. So you would see a transaction of the following form, that it requires the execution of some TEAL code, and it will only make the transfer if the code returns true, or it could do some other state changes for the blockchain. I'm hiding some details here. The TEAL code does not have to be part of the transaction. The code are stored in an account in the database so that it is referred to, but not necessarily included in the transaction. So this is a simple layer 1 language for basic smart contracts. And there are also layer 1 assets, which is at the same level as Argos. As you can see, I'm already using an example above, like the 3 USDCs from Bob to Alice. That is a layer 1 asset we can directly refer to, and the blockchain state would maintain their balances for the users. There are many other functionalities in layer 1. For example, users could register or deregister their keys participating in consensus protocol. But those things listed here are the most relevant things for the speculative smart contracts I'm going to talk about. In order for the user-defined computation to be off-chain, the speculative structure would look somewhat different from the previous picture you've seen when it was on-chain. First of all, this is the part where users still they issue transactions to the blockchain. Some are regular transactions, some are contract call transactions. The consensus committee includes them in the blockchain. But here, the difference is the following, that the consensus committee is not executing the contract calls. The only thing they do is to register the calls in the blockchain to establish the common knowledge among users that those are the calls that have been issued and need to be executed. They do something else. One thing they do, for example, is that users would prepay the execution fee at this stage, so that would be already deducted here. It is a second off-chain component that would actually execute the calls. Here there would be a new set of contract committee. The selection here is similar to consensus committee. I will talk about that more later when we get to the distributed structure. Here for a single node that belong to the contract committee, it actually runs a VM and it fetches the contract calls from the blockchain in a deterministic way. Here, simply first come, first serve, but you can imagine other scheduling algorithms could work too, as long as it's deterministic. The virtual machine will execute with respect to some snapshot of the blockchain. For example, here it runs after block 2. It will generate effects that would be communicated to the blockchain. The effect transactions are in one-to-one correspondence with the call transactions and in the same order. They are standard layer 1 transactions. So here, to process the effect transaction, the blockchain only need to, effect transaction could be payments, could be creating assets, closing accounts. So all the things that the layer 1 supports directly. Those effect transactions will be communicated to the consensus committee here via the underlying propagation network. Then the consensus committee would apply the effect transactions to the blockchain and include them in, say, block 5 as a later time after block 2, and continue with the regular transactions. And in the meanwhile, the virtual machine is executing the contract as the consensus committee continues to produce new blocks. So in this case, 2 blocks have been produced in the middle. So this is a high-level structure of the speculative architecture. Now, talking about the speculation, it's not a new concept, say, from database processing. And it does not take people long to realize that because the execution is speculative and the blockchain is evolving, there has to be a window of vulnerability. What I mean is the following, that say the execution is done after block 2, and the output of the execution is that Alice transfers 5 algos to Bob. However, when the effects appears in block 5, or the consensus committee tries to include it in block 5, Alice no longer has 5 algos, therefore that effect cannot happen, and there have to be other consequences about what's the fate of this smart contract, this contract call. So what about the progress? Because those things can be declined by layer 1. Here, again, this is not theorem proving, but this is really principles that if we think about speculation, they already happens in real life. What database is very familiar with speculation. But if you think about in real life, when we write personal checks, it takes a while for the checks to be deposited, and the balances could change and the checks could bounce. But people will understand these things, and that's why personal checks used to be so popular. Because compared with cashier checks, which is guaranteed to not bounce, personal checks does have the advantage of being asynchronous, being very flexible to issue, and you do not need to wait in line in the bank to get the cashier checks. And the hint that everybody understands is that don't write personal checks exceeding your balance. In the previous case example, Alice would have to issue payment transactions individually from her own account for her balance to drop below that 5 algos. And another point, another observation worth mentioning is that even in layer 1 with or without smart contracts in layer 1, speculations are already there. This is true for every system where transactions are asynchronously issued. but are cleared in a sequential manner. And that, because there is a gap between at the point when a user sends out a transaction and when the point that a transaction comes on chain. So when a user issues a transaction, he checks the block snapshot and be sure that, okay, the transaction is valid, but the block state may change in between. And if the transaction depends on the state that has changed, then there will be a chance that the transaction will not be finalized. Less so for payment, because payment really the individual user has to send more payments, but more so for smart contract transactions if they depend on some states that have changed in between. We rarely notice this. For example, when the chain is slow, right? The state changes are slow and rare. And when there are not too many transactions, because not so many of them would have changed the underlying blockchain state. But it has been more noticeable when the chain itself is fast, and or sometimes when the chain is congested, therefore it takes a long time for the transaction to be finalized. And the more this happens, the more likely that the transactions may bounce, even in layer 1. So the point that people have learned is how to make your transaction really not bounce. First of all, don't write bad checks because only you can move your assets. Don't depend on volatile state. This relates to how people write their smart contracts and what contract a user would want to call. To check that the contract state do not change fast and are not affected by too many accounts. And a good idea is to use escrows as needed. For example, multi-sig controlled escrows can be used when several parties want to use the same smart contracts. And script controlled accounts is something that Algorand provides in layer 1, that we can have a piece of TIL code that governs transfer in and out of account. So that's another way of doing escrow. So bottom line is that there are speculation, but speculation failures are easy to avoid when people know what to look at. Okay, so that is a bit of overview of the overall architecture, and let's dig a little bit into the single machine view from the virtual machine from a single node perspective. So this part, I would talk little about the actual language grammar. But I would focus on more about, take a non-speculative virtual machine. What components need to be added or changed in order for it to support a speculative execution? So this paradigm gives us a fair amount of flexibility so that the underlying virtual machine doesn't really, is pretty agnostic with underlying virtual machine, the programming language. So we can take whichever language we prefer and build those components on top. The first thing is some on-chain predicate, and the second is about issuing blockchain actions. Those are about how the layer 2 interact with layer 1. And the third is about the storage structure. How would the storage change in order to support speculation? The best way to understand on-chain predicate is to show an example. So let's think about this type of smart contract, automated market maker, Uniswap, if you know what it is. So this is a machine that does exchanges from between euros and dollars. And Alice inserts €1 and gets back $1.1. And that's because the machine keeps track of the market's exchange rate and when the execution is done, the rate was 1.1. But in the automated market maker, because of due to other people may also be trading dollars and euros, the exchange rate may change from time to time. At a different, relative to a different blockchain snapshot, it may determine that the rate is 1.09, for example. So what should happen if the exchange rate has changed since the speculative execution? Now, this is not an algorithmic question. This is really a policy question that can be decided by the developer of the smart contract. And that is where the on-chain predicate would come in. It provides the user a final veto power about whether the effects should really happen on the blockchain. It looks like something like this. So in this atomic transaction where the virtual machine outputs, there are two transfers, a euro from Alice to the contract account and $1.1 from the contract to Alice. And also it may include a piece of Q code as predicate. And the transaction would be considered valid only if the predicate executes true at the point when it is actually included in the blockchain. So let me give you 3 examples how the predicate may look like. For example, the developer, the writer of the smart contract may decide that I would only honor the user the exchange rate at the speculation time. So I'm going to do the exchange anyway. In this case, he doesn't need the predicate. And from layer 1's perspective, the reason why those 2 transfers happen is completely irrelevant for layer 1. Layer 1 only knows that move those coins from this account to the other account, the end. Of course, this is simple, but this also does not give the users any protection if the market is very volatile, that the exchange rate may have dropped to 0.5 and the contract may not want to do the exchange, or it may change to 2.5 and Alice may no longer want to do the change. Another policy is the following, that the developer could be very strict. It could say that I care about the rate and I would only want to do this exchange if the rate remains exactly 1.1. So the predicate will do the equality checking and fail it if it changes at all.
Jing, I have a question. So
sure.
You say the developer wants to be strict. Isn't it more the user here, the user that is wishing to do a trade?
It's a developer of this smart contract who is deciding what is the rules in the predicate. So it is like the service provider of this market maker is designing his policy about it. The users could accept the policy and call it, or could not accept the policy and does not want to use his service.
I see. So should the predicate then be somewhere central, wherever the smart contract sits? Because here it kind of looks like it's a specific choice attached to this trade, but instead it is more of a global choice.
It is a global choice in this case, that it is part of the smart contract's own code that would specify how the predicate would look like. Yeah. There is a different way. In our extensions, that's a good question. In our extensions, we are thinking about giving the users also something what we term as a post condition. So the predicate is sort of determined by the smart contract, but the post condition is something the users could provide, express the logic he wants. It's not in a prototype. It may come or may not come in the final version. That's still ongoing discussion. That's a good point. Of course, the third policy, as another example, that the developer, the decision maker here who writes the smart contracts could decide that he wants to give the user some grace range that the exchange would still happen if the rate is in this 1.05 and 1.15 range, but otherwise the exchange should not happen. So this is decided by the smart contract's own code. Well, many other things, of course. So this is how the on-chain predicate would work. In terms of the actual implementation, in Algorand, it would be implemented via the TU script. In a sense, the following, that the contract writer will be writing the on-chain predicate in the smart contract language that we provide, and the interpreter of the language would turn the predicate into TU script and include it in the transaction. Of course, there may be other possibilities. Any basic script language should potentially work. For example, Ethereum, there is a full-fledged EVM. I wouldn't recommend using the full-fledged EVM as the on-chain predicate language, because that would mean that the on-chain predicate execution cost could be as high as any smart contract, and that would still incur a high layer 1 cost. But people could determine that the on-chain predicate would only allow a truncated semantics of EVM and compile to still the EVM language, but would only use a subset of its semantics. And that would be totally conceivable if people want to do that. So any on-chain script would serve this purpose. Okay, so that's about the predicate. And in terms of how the speculative VM would communicate the output to the layer 1 blockchain, the difference is mainly about in a non-speculative VM, you can imagine the VM is directly updating the blockchain states, but in the speculative VM, it communicates by issuing blockchain understandable transactions. So example, before the VM execution, Alice has 100 algos and Bob has 50 algos. Let's say the VM's computation decides that Bob is paying 5 algos to Alice. In the non-speculative version, the VM will directly output a write set, saying that Alice now has 105 and Bob has 45. But in the speculative version, it would issue a transfer transaction that the blockchain would understand. 5 algo from, I think I flipped the sender and receiver in the example. It should be from Bob to Alice. And then layer 1 would process the transaction and make the state update. So this is simple, that we would need to install those transaction semantics into the VM so that whenever it tries to write the blockchain state, here it issues transaction. That's well understood, pretty easy understandable. Okay, the other part is about storage. So this is a third big component here. In a non-speculative virtual machine, the storage structure looks like the following. The VM has an internal memory. The memory needs to handle nest function calls and rollbacks of functions. This is particularly for smart contracts where function calling other functions are allowed, and internal functions failing may not cause the entire transaction to fail. And the outside caller may decide that, okay, I'm going to handle the internal functions error in some way, but I'm going to continue execution, but I want the internal changes made by that function to roll back. So it's well understood in transactional systems that when nested transaction could happen, we use stack structure and rollback structure in the VM's memory. After that, the VM will produce a write set, and the write set is directly going into the state database, including the blockchain database as well. I just didn't spell out. So that's right. That's a 2-layer structure from the VM to the DB. Now, speculative VM is similar in terms of the memory, but it would write its changes to a intermediate speculation cache and not directly to the DB. This is a temporary structure. That the purpose is that since the VM may execute, say, 3 contract call transactions in a row, the speculation cache should support read-my writes. That the previous contract changes should be reflected here. Then the second contract call would see those changes and build based on that. But the speculation cache is short-lived. And after the effect transactions are sent to the blockchain, this can be discarded. And upon the effect transaction appearing on chain, the write sets will be finally written into the state DB. Here, the example does not show, but in case the second transaction did not commit on chain, then the second write set will not be written to the final DB. If the third transaction is independent, does not have overlapping, the read set does not overlap with the write set, then it can continue commit. Otherwise, it will have to be re-executed a second time. So this is the speculative structure with memory, speculation cache, and contract DB. So that's another component that needs to be added in terms of the VM storage structure. There are some other changes that I'm not going to mention, but those are the the interesting things that we realize what's the difference between speculation and non-speculation, the big components. Okay, probably should finish in the next 5 minutes or so. The last thing I want to talk about is the distributed view of the speculation. Now that previously we talked about single node view, and here let's look at what the contract committee does. The contract committee in Algorand is selected in the same way as the consensus committee via VRF. So they are self-selected and their identities are hidden until they send out their voting messages. It's based on proof stake. In very much the same way as the consensus committee, except using different parameters and then at different time points. So if you do not know that selection is not really relevant. In other blockchains, if the blockchain is permissioned, they could also make the contract committee permission as well.
So Jing, I have a question. So fees for executing contract calls, are they shared between the consensus committee and the contract committee? In that maybe, I don't know, the consensus committee gets like a, I don't know, a small cut for including it in a block, and then a contract committee gets a bigger cut for executing the actual computation?
Currently in the prototype, we do not do that. We would rather reward the contract committee or really compensate their costs via the execution fees. But the consensus committee, we would rather have a separate structure. Currently, there is this flat reward rate for everybody. And later we may introduce separate incentives for them to do consensus, but we'd rather not mix up those two. Yeah, that incentive would get pretty complicated otherwise. Good question. I should probably mention that the fee is deposited at the call, and if it's not entirely used up, then the final effect transaction would refund the unused part back to you. That's just a side note. Okay, so for the selection of the contract committee, what is the condition here? The environment we want, the invariant that we want to achieve is different from the consensus. Here, we only require that if enough contract committee has voted, then at least there is one honest vote, instead of 2/3 for consensus, for example. The reason is that for the contract committee, we only need to guarantee correctness, that the final result is indeed that if you faithfully execute the VM. Byzantine agreements are not needed because the contract committee is riding on the back of the main blockchain, which achieves the Byzantine agreement itself. Now that has interesting consequences, which means that we can now tolerate in the contract committee half malicious stake rather than a third as for Byzantine agreement. That was something that we realized during our discussion, but later we found that we just reinvented the wheel. Now this is not something new in the distributed system or Byzantine computation literature. Back in 2003, people already pointed out and that you can separate execution from Byzantine fault tolerance, and one needs 2/3 and one needs a half in terms of honest users. Of course, in their study, there's nothing about blockchain, there's nothing about the proof of stake. It's purely classic Byzantine environment. But it's the same principle here. Realizing that was pretty good because it simplified the voting protocol. During our discussion, there was a while that we simply saying that, the contract committee could simply reuse the consensus committee's Byzantine agreement. And that's okay too, because we can reuse most of the system's code. But then we realized we can actually simplify the voting protocol a lot. There doesn't need to be a proposer and so on. I'll say a little bit next page. And what's more, the committee size is greatly reduced from 2,000 for the consensus protocol to around 120 for the contract committee. So this is security against what is the security guarantee for a dynamic adversary. Besides dynamic adversary, I want to also mention the validated dilemma, which was pointed out in the literature already, that if people vote and somebody could simply copy the vote without actually doing the work, that would diminish the purpose. Here we have actually two different contract committees. The validators, they vote for the results. They execute the VM, they vote for the results, but they do not review the content voted upon. An extra property is that the votes cannot be copied without knowing the content. So they cannot just simply vote, for example, for the voting on the hash of the content. That would not review the content, but that vote can be easily copied because another person can simply send the hash. So here we can simply do that. You vote on the hash of the content concatenated with this person's ID to just hide the pre-image so that the other person will not be able to reproduce the hash without seeing the content. Now, of course, when there is enough vote, the content should be reviewed so that the people know how to update the state database and how to do the blockchain update. And that is done by the second set of contract committee called listeners, who silently sitting there collecting votes, and the only job is to review the content upon seeing enough votes. So this is in the proof of stake world, where as long as both have an honest user executing, then the contract will be correctly voted and the content will be correctly reviewed. It doesn't take long to realize that this structure is also user replaceable in terms of, as in the same way as Algorand's consensus protocol, so that a dynamic adversary corrupting a validator will not affect the listener's job. So put everything together. The approach here is a mixture between on-chain and off-chain solutions. On-chain would be very simple scripting language, layer 1 assets for simple problems, and all the complex user-defined computation off-chain speculatively. It leverages a layer 1 structure for atomic state transition so that if the contract has more than one effects, we do want that all those effects are installed in an atomic way. And as I mentioned, architecture is pretty much VM agnostic. We can take a programming language that we like and build on those components to make it speculative. And in principle, this does not even need to be Algorand blockchain. It could be, a speculative structure bolted on a different blockchain and a particular VM. Just some very quick words about what kind of language that we do want. We're collaborating with Blockstack in terms of adopting or adapting their programming language called Clarity. And we do want the language to be human readable and has a modular structure, and it is interpreted so that it has smaller trust base, strongly typed and with certain safety checks, and static dependencies are very careful about dynamic dispatching, and the execution cost should be relatively easy to estimate. So that's the type of language we are currently working on. As I said at the very beginning, this is a really cross-disciplinary task, and it involves something from programming language and distributed computation and many other different fields. So it is a very different experience here. We finished the design and the prototype, and now we are working on building a formal semantics for the underlying virtual machine, and it's ongoing work. All right, I think with that, I'll stop here, and thank you for inviting. Thank you for attending. Other questions?
It seems like Ale is gone.
Early offline.
Yeah, I don't know what happened to him.
Okay, I think we are out of time also.
Okay, well, thanks, Jing.
Thanks a lot for coming. And thanks for organizing the workshop.